Just you and me, Carson.
Everyone's late arrivers.
Well, I'm not exactly punctual when it comes to class times either. There's somebody else. Oh, wait. It's
Yeah,
my,
there's you.
my alter ego.
It's actually when I was
You're in a computer lab. You're muted if you're talking to me.
I'm kind of mad that they shut the computer lab down right by the lounge and haven't done anything to it.
Oh, yeah. Yep.
It's just sitting there.
I understand.
I'm still getting this. Like, yours curves like this.
Yeah, it's a good one.
So
Is that the mic on your earphones? Are those Bose headphones?
Yeah.
I can hear
Yeah.
the two guys behind you like they're talking right next to you.
Yeah.
And I'm like, you're getting this.
Yeah,
I'm
Good and bad, I guess.
I've upgraded to a new Samsung S23, I think, about 6 months ago, and it has a USB-C port on it instead of and so now I need earbuds. I never had the wireless ones, and I'm starting to finally look for ones. And the Bose wireless earbuds look like they might be a winner to me, but it's a lot of money to invest in something you might not like.
Yeah, they're kind of expensive. You got to find ones that fit your ears right too, because some
Yep.
of them don't fit. They're not comfortable.
I didn't save that presentation. Let's see. That's probably what happened.
But I dusted off.
Hi, Joe. You got a new Casamali textbook?
Oh yeah.
You looking at the matrix analysis stuff in the back?
Yeah.
Well, if you go into grad school, you'll probably use that for other classes too. I know Rosada uses it for structural dynamics and stuff. So
I invested in it at his recommendation. So
yeah, those analysis textbooks, they always kind of irk me a little bit, like mechanics and analysis and statics, because the theory hasn't changed in the past 50 years, but they keep updating the textbooks every 3-4 years. I suppose that they do that because there's like maybe 2 or 3 pages that refer to different specifications, and the specifications change, and so they feel like they have to update. But I think it's really just a money-making scheme.
oh, probably.
Okay, let's get started. I shall share my screen. I'm going to start off by working on this computer here, my Surface with the tablet. And then I'm going to move over to my workstation where I like to do my SAP 2000 work. So some announcements. Let's see. Here's my schedule for this week. I had office hours this morning. Nobody from this class showed up. I'm giving an exam in my steel class tomorrow, so I had a couple of steel students there. But I have office hours tomorrow. Shit, that's the wrong time. Damn it! I can never get everything right. That's 11:15 to 12:30. I'll be holding office hours on campus tomorrow, so that's the right office hours. And then Thursday, Maggie will be leading this class session to give a demonstration about Tekla structural designer and ETABS. So just a word of caution. I suppose the people that need this word of caution probably aren't going to get it anyways. With Maggie leading this, that means that the session is going to be recorded on her computer. And so while I have every confidence in Maggie, that just increases the chances that that recording might not happen. You know, there's always a little quirk that could come up or whatever. So yeah, so if something happens and we're not able to record that session, then, you know, I'm sorry, that's just the way it is. I'm not going to repeat it just because it didn't record. But she's usually on top of that, and I talked to her about you know, how I have it set up, so she should do just fine with that. All right, I'm still looking for some homework number 6 from a couple of you that was due last night at 5 o'clock, but I suspect that you guys are running a little bit behind. And normally I would be firm on that, but with a small class and with me being so far behind in my grading, I'm not going to be a stickler to that so much in this class this semester. Don't tell your friends though. So what I want to do today, if there aren't any questions leading into our lecture, is I want to talk about modeling frames. That's basically the agenda. And I'm going to use a structure that some of you or most of you are familiar with in order to illustrate that. And that is what I call the Tower of Terror. So what I'll do is go to the handouts that I posted this morning on your class webpage. There were 2 of them. One is they're both PDFs, but one is a PDF of a PowerPoint and the other is a PDF of a Word document. And they're both lengthy. So I thought about possibly printing them and leaving them in the office, but then I decided to just stick with the status quo. But if somebody wanted me to print them out for you, I could do that. Just drop me an email and I can print them in the morning and leave them somewhere in the office. Yeah. All right. So this is a building that I developed, you know, 2-3 years ago as a context for some of the work that I do. It's a good context for the steel design class that I teach. It's a good context for the loads and systems classes when I teach that. It's a good context for this course as well. It's a really simple cookie cutter structure. It's ridiculously simple in that every story has a height of 12 foot 6 inches. It's a 3x3 framing plan. There aren't any openings. There aren't any inherent eccentricities, et cetera, et cetera, et cetera. So it's just a really, really simple building. So the way it's laid out, it has 8 stories, 12 foot 6 story height, uniform, 3x3 framing plan. In the east-west direction, we have moment frames, and in the north-south direction, we have brace frames. And then at the roof level, there's a 2-foot parapet. Some of these details are important for this class. Some of them aren't. Some of the details that aren't important for this class are important for the other class, et cetera, et cetera. So I try and you know, come up with different versions of these presentations that are tailored towards the different audiences, but sometimes I miss the mark a little bit. So here's a typical floor plan. And so what you can see is that in the east-west direction, we have moment frames in framing lines A and D. Oddly, the moment frame in framing line A is moment frame 2, and the moment frame that's in framing line D is moment frame 1. In the north-south direction, we have these brace frames, and I've used a double line here to indicate that we have brace frames. Sometimes you'll see other nomenclature where you can go through and have like this for a chevron brace, or maybe you would see this as a diagonal brace or whatever, but I chose to use those double lines. And so here's elevation views that we have for the brace frames and the moment resisting frames. So there's column splices in the, let's see, this is the first story, second story, third story. So there's a column splice there. There's another column splice in the 6th story. So that's where the sections change or the shapes change. And then we have the moment resisting frame over there on the right. And so I'm in these sketches, I'm trying to be rather deliberate in my symbols. So where you see the circles, we have pinned connections, and where you see the triangles, that indicates a rigid moment connection. That's not always the case. If you look at a set of steel plan sheets, a lot of times they'll The absence of any symbol indicates a pinned connection, and only the presence of a triangle indicates a moment connection. So if there isn't any symbol, that means it's just a pinned connection. But then in other cases, if you're looking at a schematic in an analysis class, for example, the opposite might be true. So in this case, I chose to use both just to avoid ambiguity. So basically, we're going to have continuity in the columns over the height of the structure. These are continuous here. And at this point here as well, and then over here, of course. But where every beam frames into a column, it's basically going to be a pinned connection, with the exception of the beams that are part of the moment frame. Where every brace frames in, I'm going to model that as a pinned connection as well. Here's the definition of the loads. I have dead load defined at the roof and at the floors. I have a curtain wall load for the envelope. I have live load specified both as a reducible and a non-reducible live load. And then we have snow load of 35 pounds per square foot. So live load reduction, for those of you familiar with ASCE 7, is challenging to implement when you go into a computer package like SAP 2000. It's challenging because the live load that you put on any given member could be reduced based on the loading that's on another member. So it's not an absolute quantity when you go and put the loading on it. So that makes it really challenging when you go in and do a computer model. And so some packages advertise that they're able to handle live load reduction, and some of them don't address it at all. Visual Analysis claims that it can handle live load reduction. SAP 2000 addresses it as well, but I basically think that that's hokey at best. That is something that is you shouldn't probably hang your hat on it. The approach that I use is that I go through and I perform the live load reduction calculations by hand, and I figure out, well, gee, on average, I'm reducing it by about 40% or 30%. And then what I do is I multiply the pressure that we have for the reducible live load by that reduction, or I reduce that pressure by that amount of reduction, and then I apply that everywhere. And so that works out to be pretty good for the columns in the building. That averaging method isn't terrible for those. But it's usually not so great for members that carry a lower amount of influence area, like a beam or a girder, which has a small influence area, a small tributary area. The amount of reduction that you can take for one of those members tends to be smaller than the reduction you can take for a member that carries a larger tributary area or larger influence area. But when we look at a steel building, we're not often using the results of our computer analysis to design the beams or the girders. We're usually designing those by hand because it's rather straightforward and we can do it without cracking open SAP 2000 or Visual Analysis. What we usually are using the software packages for is for designing the lateral force resisting systems. So the brace frames, the moment frames that are in the structure. And so in this case, those values are acceptable. I believe that's pretty much an industry standard. If you were worried about maybe being a little bit unconservative in your design, then you could apply the full unreduced live load, and that would be acceptable. But you might end up with larger beam sizes and column sizes in some cases than what you would actually need if you chased through the values. So I should also point out as kind of a throw out to Thursday's lecture coming up. This image here, this three-dimensional rendering, is actually from ETABS. And so this particular building, we've modeled it in SAP a number of different ways. We modeled it in ETABS. Maggie has modeled it in TSD and a number of other packages. So we have some good graphics associated with it. One of the things I like about TSD is that the graphics are really nice there. That's one place where it really excels. Other than that, I haven't dove in deep enough in order to really to understand how it works at the level that I understand SAP and Visual Analysis. All right, so I'm going to look at the lateral framing systems. I'm going to look at the brace frames first, and then I'm going to go back and look at the moment resisting frames. So when you get into a system like this, where it has a lot of members, one of the first things that you want to do is is come up with a naming scheme so that when you export the results, that the results make sense. If you just go in and leave the default naming, then you'll probably spend hours chasing back the results to figure out which particular member they apply to. So that's one of the first things that I want to define here. That's one of the things that I learned by trial and error, right? I mean, you learn to walk by falling down a bunch of times. And when I was getting good at this, which forgive me, presumes that I am good at it. I was, that's one of the mistakes I made was I didn't come up with that naming scheme right off. But anyway, so the naming scheme is like this. I have a column that's in framing line B, and it's in the 4th story. So that's where this name comes from right here, right? It's in the 4th story. It's in framing line B. I have a column that's in the 4th story. It's in framing line C. And if I were going to do this in 3 dimensions, a 3D model of the structure, I would also have to indicate whether this was framing line 1 or framing line 4. And so then I could add another digit to those names. And maybe I would have been smarter if I had done that here as well. But I chose to keep it a little bit simpler under the premise that these were always going to be 2-dimensional models. So here's a brace that's in the 6th story. It's on the left side of center. Here's a brace that's in the 6th story. It's on the right side of center. So I have BR6L, BR6R, et cetera, et cetera. And then I have a beam that's on floor 7. So it's a beam F7. Here's a beam that's at the roof level. So it's beam R. Then here are my node designations as well. So that's framing line B1 at the 7th floor level, or at the F7 level. Here's framing line C1 at the 7th floor level. So that's C1 F7. So that's the naming scheme. And then here are the sections that I'm using. So I went through and did a preliminary design of this frame and came up with these sections, and they should be close to being adequate. I'm not guaranteeing that they're all good, but they aren't going to be absurdly overloaded or absurdly over-designed. Right. So here is my determination of load. And this is one of the more challenging aspects of modeling a 3-dimensional structure in 2 dimensions, right? So ultimately what we're doing is this. We're taking this structure that's 3 dimensions, and we're going to construct 2-dimensional models in order to do the lateral framing. So we have this guy here, and basically we're going to come up with one 2-dimensional model of this brace frame here in framing line A. And then we're going to do one 2-dimensional model of this moment frame here. And the idea is that we use that to design the lateral force resisting systems, and then the gravity system could be designed by hand. Certainly it could be designed by the computer as well. But anyways, one of the more tedious operations is figuring out what the loads are that go on the lateral framing. And so what I'm going to do is use a tributary area approach here to determine these gravity load takeoffs, if you will. And so Maggie has a different word for it that she coined, and I like it, but I can't remember what it is now. I'll have to ask her what it is, or more likely I'll remember in about 90 seconds, and then I'll interrupt class again and tell you what it is. Anyways, so we have dead load, and for the roof and each floor level, the tributary width for the beams is going to look like that. So I have a tributary width that is 16 feet. And then I have a tributary area that will also feed into the columns that looks like that. So I have a tributary width and a tributary area, W sub T and A sub T. And so the way that this works is that, let me see if I can coordinate colors here. The blue tributary area ends up leading to this distributed load that's on each one of those beams. And then that green tributary area ends up contributing to these point loads that are here. And I'm calling them beams, but they're really girders because they are flexural members that support other flexural members. So those are actually girders, but I'll just call them beams for the sake of simplicity. Right. And so what we can do is take our distributed loads, 52 pounds per square foot at the roof level, multiplied by the tributary width. I get 832 pounds per linear foot. I can take the 52 pounds per square foot times the tributary area, I get 9.98 kips. And then at each floor level, we can do the same thing. And there you can see the distributed loads and the gravity loads, distributed loads rather than the point loads. And so the load path that's following here is that all the load that's in this blue area is traveling directly over to the supporting beam or the supporting girder there. Or alternatively, and probably more correctly, these loads are coming into this beam here, and then that beam has a reaction at the girder, and you could model it as a pair of point loads instead. So that's also acceptable. Possibly a little bit more accurate, but the level of accuracy you get out of that extra calculation really isn't justified. There's some exercises that you have done or you will do in steel design, for example, that shows that it doesn't really matter whether you model a girder subjected to a series of point loads or subjected to a uniform load. It basically ends up being the same answer. So then over here, those loads end up going out to this edge girder, and then they go here and then into a point load that is applied to that column. And since I'm not modeling this beam, this girder here, I'm going to have to model the loads that are transferred into the column from that member instead. And that's where that 9.98 kips or 12.5 kips come from. All right, so with that explanation, then the next step is to look at the snow load at the roof level. Similar process, except that we just have smaller loads, a distributed load of 560 pounds per linear foot and point loads of 6.72 kips. And then we can do the live load at each of the floor levels. So here's my tributary width again, my tributary area, that remains unchanged. And then if I assume a 60% reduction on average, that takes the 80 pounds per square foot to 48 pounds per, there's a units issue there. It's funny, I've been given this presentation for a couple of years and I still find mistakes in it. And so then I take that 48 pounds per square foot, gives me 768 pounds per linear foot on each beam, and then 9.22 kips at each column level. All right. So then the next step is to look at the curtain wall loading. And so what I'm doing in this case, let me go back to my slide where I dictate the loads. The curtain wall has a load of 45 pounds per square foot that's applied to a vertical tributary area. And so we assume that that loading is equally distributed to the floor or roof levels above and below each story. So now let me go back and to this slide. And so now I'm going to look at an elevation view of the frame that is in framing line number 1, including the gravity framing. So there's an opportunity to illustrate. So this is the lateral force resisting system here. And this frame right here is just to carry gravity loads, and this frame right there is just to carry gravity loads. So that's what I mean when I say gravity framing versus lateral framing or lateral force resisting systems. So if we go in and look at the tributary height and the tributary area at the roof level, that blue area is going to be translated into a uniformly distributed load along the length of the beam, pounds per linear foot. And then is going to, the green areas that are shown here are going to translate into a point load or a concentrated load that acts at the column, either column B or column C at that level. And then so we can do the same thing for the tributary height and the tributary area at each floor level. A little bit different because the roof has a 2-foot parapet above it instead of half of a 12-foot 6-inch story above it. And so we can calculate those heights and those tributary areas. And so when we go through and calculate our loads, we end up with 371 pounds per linear foot on the beam at the roof level, 4.46 kips at the columns at the roof level. And then at each floor level, we end up with 563 and 6.75 respectively. All right, so this is a summary of the loads, of the gravity loads that I have on those brace frames, right? So I have dead load on the left, I have the curtain wall load next to that. To the right of center, I have the snow load at the roof level, and then all the way to the right, I have the live loads. So the curtain wall load is technically a dead load. So when we apply our load combinations and our load factors, I'll use the same factor on the curtain wall load that I do on the dead load. I usually tabulate them separately though. I keep track of them separately. That way, when I find a mistake and I need to go back and chase that through my numbers, it's easier to do that when I have the curtain wall load calculated separately from the dead loads that are applied or part of the roof and the floor slabs. Excuse me. I've done this a number of times with a number of different buildings. Every couple of years we change the capstone project, right? And so I have to do this all over again. And I never get it right the first time. It just, I mean, it's tedious. I'm anal retentive, but even with that, I still screw it up every time. Anyways, right. So there's the loads that we're going to put on. Gravity loads. We still need lateral loads, but I'll come back and hit that at the end. So here's the moment resisting frames. Same idea that we did with the brace frames, except now we have fewer members. And so if we go through and do our gravity load takeoffs, in this case, when we look at the tributary width, it's much smaller because the beams that are part of the moment resisting frame are parallel to the floor joists or to the filler beams in the structure. So the tributary width is only 4 feet on those members. Then if we look at the tributary area that goes into manifests as a point load in the columns, that has a goofy shape in this case. And the reason why, let me go ahead and show you what that area is. It's 320 square foot per column. And the reason that is a strange shape is because any load that's acting to the left of center of that girder is going to come over and act as a point load there, plus the reaction force that comes from everything on that half of that beam. So all of this load ends up making its way either directly or indirectly into that column. And so that's why it's a goofy shape. Now, I guess that's all I had to say about that. So if we look at the roof level, we have a dead load of 52 pounds per square foot that ends up as 208 pounds per linear foot on the beam, or 16.6 kips at each column. And then at each floor level, it works out to be 260 and 20.8 instead. Okay, use the same approach for the snow load at the roof level. We get 140 pounds per linear foot, or 11.2 kips. We can go through and look at the live load at each floor level. Again, similar, 192 pounds per linear foot, or 15.4 kips at each column location. And then the curtain wall loading. This is remarkably analogous to what we did with the brace frame just a moment ago. So the blue tributary area, these are vertical areas. The blue tributary area ends up being a distributed load on the beam, and the green tributary area ends up being a point load at the column locations. Different tributary heights at the floor levels relative to the roof level. And so with the curtain wall loading, we end up with these loads. All right, so there are the loads that are on our moment resisting frames, the gravity loads. Now for the wind load, if you guys aren't familiar with ASCE 7, then this is going to be foreign to you. But even if that is the case, really all we need are the loads that are coming up a few slides from now. That's all we need for this class. If you're interested in learning more about this, then take loads and systems. It's currently an undergraduate level class, but there's talk of making it a dual level class sometime in the future. I'm not sure when. That's administrative. Anyways, we're basing our wind loads on a base wind velocity of 115 miles an hour. I've assumed exposure B. We have a directionality factor of 0.85, an elevation factor of 1.0. Gust factor of 0.85. The premise is that this building is designed in the Cincinnati area. Cincinnati has an elevation above sea level of around 800 feet, depending on where you're at. So we could take an elevation factor, a reduction of like 4%, but it's just not worth my time to calculate that. I should also mention that when I calculated these, it's based on the ASCE 716 criteria. And it is a little bit different in the ASCE 722. Not a whole lot different, not enough to really influence anything we're doing in this class, but in case you start chasing numbers or something, then that might make a difference for you. One other thing that's a little bit different for a cookie cutter building like this one that's rectangular in plan, you don't have to consider eccentricity of the wind load acting on the structure. But I decided to do so anyways to make this problem a little bit more interesting. So I'm assuming that we have 15% eccentricity in the application of the wind load, ignoring the stiffness of the transverse lateral framing. I should wonder about including that word in my lectures nowadays. Right, so here's the spreadsheet that I use to calculate wind loads. After you come up with the velocity pressures, the Q sub Z terms, then everything else is really easy to do in a spreadsheet. And so that's the way I usually approach these after I get through the first couple of examples in the loads and systems class. So in the east-west direction, these are the moment resisting frames. In the north-south direction, these are the braced frames. And so you have a force on the windward wall, a force on the leeward wall, and then the net, the combination of the two. And so at the roof level for the entire structure, I have 23.7 kips blowing in either the east or the west direction. And then if you add up those wind loads over the height of the structure, the total base shear in the east-west direction is 196.7 kips. And similarly, in the north-south direction, I have a force on the windward wall, force on the leeward wall, and a force at the roof level of 32.6 kips for the entire structure. And that gives me a base shear of 277.8 kips. Note that the parapet loads are handled a little bit oddly. Those of you who had loads and systems, you should be familiar with this, but those parapet loads are translated down here and are applied at the roof level. The next step is to do a horizontal analysis to figure out how much each one of the lateral frames carries. And so the takeaway from this is that for the braced frames in the north-south direction, each one of them carries 65% of the total applied load in the north-south direction. And for the moment resisting frames in the east-west direction, each one of those carries 65% of the total applied lateral load in the east-west direction. So again, this is just a one slide that talks about something that I spend a week on when we're in structural loads and systems, how to do the horizontal analysis. Not something I can spend a whole lot of time on here, but in short, what this does is it takes the center of rigidity of the structure, which is somewhere here in between the two moment resisting frames, in between the two brace frames. And what it does is it accounts for the prescription that our east-west wind load is applied with some eccentricity, or that our north-south wind load, I'll draw that in instead in green, is applied also with some eccentricity. And so the idea is that when we take those loads that are applied eccentrically and we apply them concentrically to the center of rigidity, that they come along with some force and some torsional moment. And so in this case here, that force is translated out to this frame and to this frame, and that moment is translated outwards like this. It's applied in this direction on that frame, and it's applied in that direction on that frame. So you end up with one of the two frames carrying more than its fair share of load because of the eccentricity, because of the in-plane torsional moment that exists. So the takeaway from that is that if we go back a couple of slides, what I'm going to end up doing is multiplying these guys. Let me go to a different color. So I'm going to multiply this guy here by 65%. So I have 23.7 kips at the roof level multiplied by 0.65. And get my calculator real quick. So that gives me 15.4 kips. I'm going to take this guy here, 32.6 kips, and it's also 65% for the brace frames. And so let's see, 32.6 times 0.65, that gives me 21.2 kips. So when we go ahead a couple of slides and look at the loads, I have 21.2 kips. Whoops. I have 21.2 kips here for my lateral load at the roof level on the brace frames, and then 15.4 kips here. Okay, excuse me. All right, so what I'm going to do now is I'm going to jump over to the other computer, and I'm going to start working in SAP 2000. I have models of this in visual analysis as well, but I'm not going to do it in visual analysis in class. I'm going to stick to SAP 2000 for this, and then we're going to move on and model it in ETABS as well. And so visual analysis was nice for me because frankly, it does a pretty good job of doing design checks. It's easier to interpret than SAP 2000 for small structures like this, and that's why I did it. But I'm not going to require you guys to do that. And so, anyways, let's see. I've got SAP running over here. Let's see, I need to share my screen. Screen 3. All right, so here's SAP 2000, and what I wanted to also do was bring up that same PowerPoint presentation so I could Alt-Tab between. I need to save it over here, otherwise I'll get a conflicted copy with the two computers. Now I need to wait for Dropbox to upload it. Now I need to wait for Dropbox to download it. Can you imagine what it was like when we used to teach these classes 20 years ago with transparencies and all that other shit? What's a transparency? That's what Ben wants to know, or what Carson wants to know. Sorry, I don't know why I keep calling you Ben. I don't know. That's probably because Ben Carson. He was a politician that was running for president a few years ago. I think that's stuck in my head. Anyways, right. So here's our building. So what I'm going to do is go to this slide here and use this for the geometry. One thing I'm going to model the brace frame first. It's a little bit more interesting. So the brace frame has a bay width of 24 feet. So, and then it has story heights, right? So that's what I'm going to go for. So the first step is to come up with a grid. So I'm going to define this as a grid only, and then I'm going to customize that grid. So in the X direction, let me see if I'm going to model this the right way. It's actually going to be in the YZ plane. So I can do that. Let me specify these in the YZ plane. So in the Y direction, I want, let's see, I've got 1, 2, 3, 4 grid lines. In the X direction, it doesn't matter. I just need 1. And then in the Z direction on the next slide, come on, next slide, please. I need 1, 2, 3, 4, 5, 6, 7, 8, 9 grid lines. So let me go here. So in the X direction, I just need 1, I need 4, and then 9. The X direction spacing doesn't matter. The Y direction spacing is 24 feet. The Z direction spacing is 12.5 feet. And my first grid line is at 0, 0, 0. Okay, and that should, I think, give me what I need. So let me keep this as a 3D view on the right. On the left, I'm going to go to the YZ plane. There we go. And so now I have, is that right? Well, it didn't label the framing line right. So I can go in and edit the grid, modify show systems. So the grid ID in the X direction is going to be ID number 1. And then here, I want this to be at 0 is going to be A, at 24 is B, C, and D. So my origin is down here at grid line A1. And so this is going to be A, that's going to be B, C, and D, like that. Okay, I want this to be the ground floor. I want that to be F2. I want that to be F3. I want that to be F4. I want that to be F5, F6, F7, and I screwed up something. F8, I did not screw up something. F8, whoops, that's 9, and then R. All right, and so hit OK again, and there we go. Great. So the only thing it's missing, for some reason, it's not showing the elevations, but I'm going to run with that and call it OK. All right, so what I'm going to do is this. Let's see, I want to define my cross sections. And that's important because it's easier to define them up front. So I need a 1272, a 1253, and a 1240 to start off with. So let's define section properties, frame sections, import, W shape. It's going to open up this library. I'll use the 15th edition of the manual. Okay, so I need W1272. What was the other ones? W1272, 53, and 40. Okay, what do I need for beams? 1835 all the way up to the roof, and then 1631. There's the 1631, and there's the 1855. Hit OK, hit OK, and OK. All right, so now what I'm going to do is draw in my columns. So the columns at the base level are a W12 by 72. I always start at the bottom and draw upwards with my columns. I'm only going to draw the first story columns. I must hit the wrong button. There we go. Now I'll draw the column here, 1272. The framing is continuous because the columns are continuous with each other. Now I'm going to draw that beam in. The beam across the top is an 18 by 55. This framing is going to be pinned because the beam is pinned to each one of the columns. Then I can go in and show the releases just to make sure that I have everything defined the way I want. There we go. Now I need the braces. The braces at the ground level are HSS 66 half. So I'll go back in and define my sections, frame sections, import property, a tube. And so I need 66 by half at the lower level. These are tedious. These, I always wish they had done this better because they have them sorted by section size. But the way they have it is such that a 3/16 is bigger than a half because a 3 is bigger than a 1 in that fraction. And I always thought, well, gee, you guys could do better. And they just don't. So here's a 6/6 by half. What else do I need? I need a 6/6 3/8, a 5/5 half. Let's see, 6/6 3/8, 5 by 5 by half. There we go. What else do I need? I need a 5/5 3/8, 4.5 4.5 3/8. Okay, then we go up here, the 4.5 4.5 3/8. So the 4.5s are actually smaller than the 4s on this. And then I need, yeah, that's it. That should do us fine. Hit OK. All right, and so 6 by 6 by half at the ground level. So let me go ahead and put these in. So this is going to be a bit of a problem because I need to frame these in at the mid-length of that beam, and I don't have a framing line there. What I could do is put one in. Let's do that. I think that's probably the best way of doing this. Let me go and edit my grid data, modify. And so I'm going to come in here and I want to add a grid line. And so this is going to be, I wonder if it'll let me do this, B.5, and this is going to be at 36 feet. Line type secondary, and the bubble location, we'll put it at the start. Yeah, it showed up. Okay, good. All right, so now I can come in and draw those braces. And just like I do with the columns, I'm going to start at the lower end and go to the upper end in all cases. Okay, and so let me go back to my display options, show the sections, make sure I have those defined the way that I want. Okay, now a couple other things. What I'm going to do is I'm going to copy this vertically. And when I do that, it makes a lot of sense to have the parameters defined before I copy. So I want to set the beam so it's automatically meshing. I want to set the output stations the way that I want and that sort of thing. In fact, if I wasn't pressed for time, I would actually go through and define the loads on this as well, but I am kind of pressed for time, so I won't do that today. Let me zoom in a little bit down there. It's not quite what I wanted. Let me see if I can hit that button instead. Yeah, it's zooming in on the. All right, so let me go in here and select that beam. I'm going to go to assign frame, and I'm going to go to automatic frame mesh. And so what I want to do is mesh at intermediate joints. Otherwise, it's not going to connect these two braces to that beam. If I want these two braces to connect to that beam, then I have to automatically put a node in there. So I need it to auto mesh at intermediate joints. And let's divide that up into a minimum number of segments. If I'm doing a beam design in structural steel, I'm going to need the moments at the quarter points of each unbraced segment so I can calculate C sub B values. There's going to be a brace at the middle, so let's just go ahead and put in a minimum of 8 segments, and that'll give me M. And so that would be okay there. I might have chose this differently the last time I did it. For these columns, I'm okay with, there we go. And that one, I'll do the same thing there. The columns, I don't need to break those up as much because they don't have any intermediate transverse loadings. There's lateral loads, but they're all applied at the floor levels. I don't need the intermediate joints, but that won't hurt me either. And so we'll go like that and then hit OK. All right, and so now what I'm going to do is I'm going to copy that vertically. You go up here, I think it's F3. Yep, zoom extents. Let me drag a window, and I want to copy that upwards. And in order to do that, it's actually a replicate command in SAP 2000. So we're going to go up here to draw, and then we're going to go to, maybe it's under edit. We're going to go to edit. And then we're going to go to replicate. I usually hit Control R. So I'm going to go in increments in the Z direction, and it's going to be 12.5-foot increments. I want to have 1, 2, 3, 4, 5, 6, 7 copies. And so that's going to basically copy that upwards. And then, there's a lot of other things you can do. You can do this in a radial way. You can do it using a mirror if you want. And then you can go here and open this options data dialog box. And you can choose to include or exclude things like releases, local axes, cardinal points, skews, output stations, loads, all kinds of stuff. So if you want to copy some stuff but not other stuff, it's all in here, right? And so here's the loads. I don't have any loads defined yet, so it's all grayed out, but I'm going to leave that as a default. I'm going to go ahead and hit apply, and there's my structure. All right, so it doesn't look too bad. Let me go here to display, and there's a way of refreshing this. So right now I've got more than one thing displayed on here. I've got my automatic meshing displayed as well. So there's a refresh button. Sections, releases. That didn't work. Where is it? Huh. Well, I'm not going to take the time. There was a way of refreshing the display because get artifacts like that. Let me do this. Let me try this. I'll get rid of the sections and the releases. Hit apply. There, I've got yes. I can go in here. Let's show the analytical model. It has to create the analytical model. And now if we go back and look at the nodes are currently invisible. Let's make them visible. See, it put all those extra nodes in the beams. It put the extra nodes in the columns. And now the braces are supposedly connected to the beam. All right, let me go back here. I don't want the analysis model very bad anymore. I do want sections though. Let's keep those nodes invisible for the time being. And still has the S in there. So what I need to do at this point is I need to split the columns and put the different column sections in. If I'm being anal retentive about this, I'll actually divide the frames up and splice it 4 feet above the deck or 4.5 feet above the steel sections. I'm just going to for lack of time, I'm just going to change the cross sections. So stories 3, 4, and 5 are going to have the W12 by 53. So let me go in here. Stories 3, 4, and 5 there. Stories 3, 4, and 5 here. I'll go to assign, frame, sections, and that's going to have the W1253. And then for the upper 3 stories, stories 6, 7, and 8, they're going to have the W12 by 40. So there and there. And then hit apply. Whoops, I needed that dialog. Let's go to that roof beam. We'll go to assign frames, frame sections. That roof beam is actually a 16 by 31. Okay, go like that. And now we need the braces. And this is where it gets a little bit tedious. As the story shear decreases going up through the building, then the size of the braces also decreases. So in the 8th and the 7th story, I have 4. Well, in the 8th story, I have 4 by 4 by 3/8. I didn't include that section. I need to come back and get that. Let me go here, define sections, import HSS 4 by 4 by 3/8. There it is. Okay. Thank you. There we go. Hit apply. Shit, that wasn't what I wanted. Hit apply again. There we go. HSS. Now here I want 4.5 by 4.5 by 3/8. Okay, at the next level, so 2 levels, stories 5 and 6, I've got 5, 5, 3/8. So I've got these braces here and these braces here, 5, 5, 3/8. Apply. Then I've got 5 by 5 by half for 2 stories. And then I've got 6 by 6 by half. Right. All right. So then I could go through and put my gravity loads on and then my lateral loads. I'm going to go to the lateral loads now because I don't have time to do it all. And the lateral loads are going to be more interesting. So let me go through, define load patterns. I've got my dead load defined. I'll save that with a multiplier of 1. So I'll modify that. Let's call this W. And it's the wind load. So I'll change that to wind. I'll add that. I'll just go ahead and put curtain wall, live and snow in here at the same time. So the curtain wall goes in as a dead load. The snow load goes in as a snow load, and the live load L goes in as a live load. All right, like that. So now what I'll do is I'll come in and assign joint loads, joint loads, forces. And so I want to assign the wind loads. And so these are going to be, I'm in the YZ plane. So these are going to be in the positive Y direction. Actually going to be, let's see, this is framing line A. So if I want them to point to the right, it's got to be a negative. No, it's got to be a positive number. Okay. So what are the magnitudes that I need here? Go here, go to the end of my lateral loads there. Get rid of that ink. So I need 21.2. I hit apply. There we go. Now I'll select the next node. That's got to be 23.9. Hit apply. And the next one is 23.3, 22.6. $21.8, 28. Then I have here 19.6 and 18.2. Okay, I need to restrain the nodes at the base. So I'll go to assign joint restraints. I'll call them pinned like that. I need to set my analysis options so that I model it as a 2D frame. So set analysis options. Got to be careful here because if I just select a plane frame, it assumes that the frame is in the XZ plane, and that's not what I want. So I want displacements in the Y direction, displacements in the Z direction, and rotations about the X axis. So that is the plane frame definition that I want. Okay, and so let me go ahead and save this as something. I'll go to my temp directory that I've been using, this class. I'll call it Tower of Terror 2D brace frames. And I'll just give it a version number just in case I modify something. Okay, let me go in and do my analysis now. And okay, so there's my deformed shape under dead load. Let me go ahead and plot the deformed shape here under wind load. I didn't put any dead loads in, so it makes sense. All right, so it's moving the way that I expect. Let me go over here, and in this right view, I'll set that up in the YZ plane as well. I'll go and draw diagrams there. Since we only have wind load, I'll go ahead and draw a wind load diagram. I'll use axial force because it's a brace frame, so it's going to be dominated by the axial stiffness. And so you can see the stiffness of those load, the impact of those loads. So we have tension in the braces on the left side and compression on the braces on the right side. So let me do this. I'm going to go over here and show the nodes again in that model. And what I want to show is this. Let me change the units to inches. So if we look at the roof drift at this node here, we have a drift in the Y direction of 2.4355 inches. If we go over to this node, we end up with a drift of 2.424 inches. So if we were modeling this in 3 dimensions, well, in a real building, if there were a drift, we would expect those two nodes to have the same amount of horizontal displacement, but they don't. And the reason why is because that beam that is at the roof level actually shrinks in length a little bit under the compressive load that it carries. See how it's carrying compression here and a little bit of tension there? So that beam actually changes length. So we have a couple of different options to make this model more reflective of what we expect in reality. The reason that we would expect those two nodes to displace by the same amount is because we would expect there to be a concrete floor slab or a concrete roof slab, and it would have basically a very high stiffness in plane. So one approach is to go in and select all of these beam members and specify a property modifier for the axial of 0.999999, or not point, but 999. So I can go in, assign frame property modifiers, and for the cross-sectional area, I can specify a property modifier like that. And then sounds like there's helicopters outside. If I get taken away in handcuffs, then somebody stop the recording. Let's go ahead and run it again. Okay, now we look at the displacements over here on the left. On the left side of the frame, we end up with a displacement. Come on now. Thank you. 2.3051 inches, and over here, 2.3051 inches. So that accomplished what we wanted, but it's not as sophisticated as we could have. It works, and the results that we would get out of it would be okay, but I'm going to show you a different way. Let me go through first and remove those. So I'm going to go in those property modifiers and I'm going to specify 1 for everything. So that gets rid of the property modifiers that I just defined. What I'm going to do instead is I'm going to define something called a constraint. I'm going to go in and define a joint constraint. And what I'm going to do is use a diaphragm constraint that's going to tell SAP 2000 that, hey, this is a building that I'm modeling. The real building has diaphragms in it that keeps the horizontal displacements at each one of those nodes equal to each other at every Z elevation. So I'm going to add that new diaphragm constraint like this. The constraint axis is going to be the Z axis, and that's an axis that's normal to the plane of the diaphragms that I'm defining. So the diaphragms are basically the floor slabs and the roof diaphragm in the structure. The normal to those diaphragms is going to be the Z axis. And I'm going to check this box down here at the bottom that says I want a different diaphragm constraint at every elevation in the structure. So let's go ahead. I'll just leave the constraint name as its default. And I'm going to go ahead like that. And then I'm going to hit OK here. And so what it's doing is for each one of these nodes that's selected, it's going to go figure out what the Z coordinate is. And for every group of nodes that is at the same value of Z, it's going to assign a constraint that says that every time one node moves by a certain amount, the other node has to move by the same amount. And so we hit OK like that, and we give it a minute to think. I hope this works. I don't always get this right the first time either. All right, and so let me, oops, that's not what I wanted. I wanted the escape button, not the, there we go. If I go in and right click on that node, it brings up this modifier and it says constraints none. All right, that's not what I wanted. So that's why let me select those nodes again. Let me go to assign joint constraints, and I'm going to assign the constraint to those nodes. Hit OK. And so now I can go in, right click on those. And so I have a diaphragm 100. And so that's the constraint that node participates in. Let me go here. This is going to be diaphragm constraint 87.5. So the 100, the 87.5, that's the Z elevation of those nodes in the units of feet. So let me go ahead and run this model again. And so now if we go through and look at the lateral displacements, come on. There we go, 2.3051 and 2.3051. If we check it down here, 0.6049 inches, and then over here, 0.6049 inches. So there's a couple of things. We're out of time. The couple of things, we introduced the idea of calculating gravity loads on a lateral frame. We modeled a brace frame real quick. We put the lateral loads on it, and I introduced the idea of a constraint. So there's still some more to go here. Maggie's going to jump over and do some work with this structure in Tekla Structural Designer and then in ETABS on Thursday. When we come back next Tuesday, I'll come back here to SAP 2000 and we'll continue tinkering in 2 dimensions. And then the 2 ideas will merge someplace late Tuesday or early Thursday of next week. So, all right, I'll stick around for a few minutes to answer questions you guys might have. Otherwise, I'm available tomorrow at 11:15 for office hours, or Maggie's going to have class again online at 12:30 on Thursday. All right, thanks.